Good morning. This is Analog Circuits 18EC42, Module 3, Lecture 2, Part 1, Output Stages and Power Amplifiers. We are discussing today about the Class B. In the earlier class, we considered about the need for the power amplifiers, also the classification of the power amplifiers, and then the Class A power amplifiers whose efficiency is very small, and which conducts for all the 360 degrees cycle. Today we are discussing about the Class B power amplifier. So the Class B output stage consists of complementary pair of transistors. We have here two transistors QN and QP, so complementary and a pair of transistors connected in such a way that both cannot conduct simultaneously, or rather this conducts during the 180 degree cycle, and in the other half of the cycle this conducts. When the input voltage Vi is 0, when this is 0, we see that both the transistors are off, cut off, and V0 will be 0. So under quiescent conditions, that means 0 input signal conditions, the output will be 0. When the input is 0, the output is 0. When Vi exceeds the 0.5 volts, this value becomes positive 0.5 volts. Then Qn conducts. This will conduct and it will act as an emitter follower. The output is taken out at emitter and the input is given at base, and you have at the collector VCC, hence this will act as a emitter follower. So when positive is there, this PNP will be off and the NPN transistor will be on. So V0 will be just followed by V0 will follow the Vi. Only difference is the value, which is V0 is equal to Vi minus 0.5. So that is why if it is more than 0.5, VBE rather, V0 is equal to Vi minus VBE, and if the VBE value is above 0.5, then when the input value is above 0.5, then the Qn starts conducting and the QP will be off. When Vi goes negative, that means this Vi is negative, then Qn will be off and QP will be on, and that negative voltage should be more than 0.5 volts. So QP conducts and operates again as a emitter follower, and V0 follows Vi, Qn will be cut off. So you have a band here from minus 0.5 to plus 0.5, which we generally call it as dead band. So thus we can see that here, for 180 degrees cycle Qn operates, for the rest 180 degrees cycle, that is positive cycle Qn operates, negative cycle the QP operates. Because of this reason, the circuit is set to operate in the push-pull fashion. So now this range of values of the input between minus 0.5 to plus 0.5 during this portion, both the transistors are off. When the input is between minus 0.5 to plus 0.5, both the transistors are off, and hence it is known as a dead band. It is known as the dead band. And in the rest of the thing, we'll have the characteristic which is like this. That is, the output will follow the input. The output will follow the input. So when the input is 0.5, the output will be 0. When the input is again minus 0.5, the output will be 0. But once the input goes above 0.5, the output will just follow, will have a slope which is correspondingly 1 till the time saturation of the transistor is reached. That means when the output becomes VCC minus VC sat. So when the output becomes VCC minus VC sat, at that time the input should have been VCC minus VC sat plus VBN. So unless this is not equal to this, that is VCC minus VCE sat plus VBEM, the output cannot reach VCC minus VCE sat. Similarly, in the negative portion also, it is just the same. The saturation point for the P type of transistor will occur when the output is VCC plus VEC P sat. And that should be, definitely correspondingly, we should have, the voltage across the emitter to this junction to be, more than the magnitude wise, more than the minus 0.5 volts. And that should be definitely subtracted. When the input is minus VCC plus VECP sat minus VEPP, then the output will be minus VCC plus VECP sat. And during this time, we have the QP conducting. So QN conducting during this portion, QP conducting during this portion. So if you put the input characteristic here, input waveform here, and the characteristic here, we'll get the output waveform here. So where we'll get, because of the dead band, we'll get these two portions over here, right? Where both the transistors will not be conducting. During this portion, Qn conducts. During this portion, Qp conducts. And during the small portion here, none of the two are going to conduct. So neglecting the deadband portion always, we can consider that the average load power will be PL is equal to, again, it is V RMS square by RL, and that turns out to be, V naught square, where V naught is peak, V naught square by 2 RL. So V RMS square by RL will be the value of PL. VRMS is equal to V naught by 2, and therefore PL will be equal to 1 by 2 V naught square by RL. The average current drawn from each of the two what you call power supplies will be just corresponding to. So the plus VCC, will be the power supply which will from which this current is drawn, and minus VCC is the one from which this portion of the output voltage is there, and correspondingly the current. So corresponding to this output waveform, we'll just, if you divide this by RL, you'll have the current. If your output voltage is this, current will just correspond to dividing this by RL. So the waveform for the what we call current, which is IL, or indirectly the current which is IC, will also be just the same. So during this portion, if you see this here, the average of only the half wave. So this is the half wave current which will flow through each of this, will flow through Qn, and this will flow through the negative half, will flow through the Qp. So if the average value of the Qn which flows through the what we call Qn will just correspond to the value, the current. If we calculate, it is I average is equal to 1 by pi V naught square by RL. Hence, the what we call power which is supplied by the two different sources, that is positive as well as negative, will be 1 by pi V naught by RL, that is the current, which is I average, multiplied by VCC. So total power will be the PS plus equal to PS minus. Together we should add this, and you will get the value which corresponds to the twice of this value over here. So PS will be PS plus PS minus. So total power supply will be this much. Thus, the power conversion efficiency will be PL by PS into 100. Neta is equal to PL by PS into 100, and this divided by this will give us pi by 4 V naught by VCC. The maximum value V naught output voltage can take is the VCC. Output voltage will be definitely less than VCC. Rather, maximum value of V naught is VCC minus VCE sat. V naught is VCC minus VCE sat. So maximum value of neta will be, if both are same, if we neglect VCE sat, if both are same, then it will be pi by 4, and that pi by 4 will just correspond to 78.5%. So the maximum efficiency is obtained when V naught is maximum, and that is VCC minus VC sat is equal to VCC. At this value of the peak output voltage, we will have the what you call the neta maximum efficiency, the power conversion efficiency to be pi by 4 equal to 78.5. So whereas in class A, it is just 25%, in the class B, it is 78.5. So you can see that the performance of the class B is far better than the class A. So the maximum average power available from the class B output stage is PL is equal to, VRMS squared by RL, and that is equal to half of V naught squared by RL. We already said that when input is 0, output is 0. So therefore, the quiescent power dissipation of the class B stage is 0. Quiescent just corresponds to when input is 0. So input is 0, output is 0. So when an input signal is applied, the average power dissipated in the class B stage is PD is equal to PS minus PL. PS we know 2 by pi, V naught by RL, VCC, PL we know 1 by 2, V naught square by RL, and if you subtract both, you get PD. Now, when will this be maximum? The maximum average power dissipation will be when we differentiate this with respect to V naught and then equate it to 0, then the value of V naught will be, so you'll get, if you differentiate this with respect to V naught, then you'll get 2 VCC by pi RL minus 2 V naught by 2 RL. So 2 will cancel. And if you take this term on the other side, you'll just get V naught by RL is equal to 2 by pi RL into VCC. And that will give us the RL cancelling, and we will get the V naught is equal to 2 by pi into VCC. Right? We will get V naught is equal to 2 by pi into VCC. So if you substitute this in this equation, that is V naught as 2 pi by VCC and V naught is equal to 2 pi by VCC, we'll get this as the value which is, we'll get this value here. V naught is equal to 2 pi by VCC means 2 square by pi square. So this quantity will become, this quantity will become 2 into VCC by pi. So 4 by pi square VCC square by RL. 4 by pi square VCC square by RL. And if you substitute 2 by pi over here, then we'll get 2 by pi square VCC square by RL. And the result will be PD max is equal to 2 VCC squared by pi squared RL. So this is the maximum power dissipation. And naturally, half of that will just correspond to power dissipation by each one of those transistors. So this is the total one. This is the total one dissipated by both the transistors together. Each transistor will dissipate half of this, that is VCC square by pi square R. And that is what is written here. And the overall graph of the V naught versus the power dissipation is like this, and the peak occurs corresponding to 2 VCC squared by pi squared RL when the efficiency is, so at this time the efficiency will become the value 50%. That is because if you try to substitute this V naught in the equation corresponding to that, that is over here, V naught is equal to 2 by pi VCC, then definitely that will become 50%. So 2 by pi VCC, if you substitute for this, pi will cancel, 2 and 4 are left, so it will just be half of it. VCC also will cancel, and that will become half. So thus, at the maximum power dissipation, the efficiency is only 50%, but later when the output becomes equal to VCC, we will have the efficiency theoretically as 78.5%, but however, it will be a little lesser than this. We can almost consider 75%, 70 to 75%. It is now let us take a numerical associated with this. It is required to design a class B output stage to deliver an average power. Average power is this. Okay, average power is this. Average power is the PL itself to a 8 ohm load. The power supply is to be selected such that VCC is about 5 volts. VCC is 5 volts greater than the peak output voltage. Okay, VCC is about 5 volts greater than the peak output voltage. This avoids transistor saturation and associated nonlinear distortion, allows for including short circuit protection circuit. Determine the supply voltage required and the peak current drawn from each supply, total power supply, the power conversion efficiency. So we need to determine the supply power required, the peak current drawn from each supply, the total supply power, and the power conversion efficiency. Also, we need to determine the maximum power each transistor must be able to dissipate safely, that is PD max for each of the transistors. So we know PL is equal to half of V naught square by RL. So V naught will be root of 2 PL RL is equal to 17.5 volts. So we are able to get the value of the V naught, which is approximately 18 volts. So VCC should be 5 volts above. So therefore 18 plus 5 will be the safe value to select for VCC is 18 plus 5 equal to 23 volts. So the peak current drawn from each supply will be I naught is equal to V naught square by RL, V naught by RL, and V naught we have calculated here as 17.9, and that if you try to substitute, you will get 2.24 amperes. The average power drawn from each supply is PS plus equal to PS minus, and that is equal to 1 by pi V naught into this is I naught into VCC. I naught into VCC. You can find in terms of I naught, or you can write in terms of the total power PS minus PS plus. Also from the formula which is written here. Okay, we can write from here also, or we can write the formula corresponding to that. So it will be 1 by pi 2.24 into the value of 23. That will give us 16.4 watts. This is the PS minus and PS plus. So PS plus PS minus together will become 32.8 watts. So the power conversion efficiency will be PL, we know, given 20 itself, and PS is double of this, that is 32.8, and that is what is written here. So we will get 61% efficiency. So the maximum power dissipated in each transistor is given by PDN max equal to PDP max is equal to VCC by pi squared RL, and VCC we know 23 squared divided by pi squared, RL is 8 ohms, and we'll get 6.7 in each. Together in both the transistors together it will be 6.7 into 2, that will be 13.4. Now we have here the what is known as the dead band, which leads to crossover distortion. Okay, this is dead band which leads to crossover distortion, and this should be reduced. How do we do that? So there is a method wherein we just try to give a high gain op amp at the input side, which will be able to reduce the what you call crossover distortion. Again, we are just providing here a negative feedback. We are just providing a negative feedback. So this amplifier for all the practical purposes will just give you the amplification which is 1, because it's a you know, unity gain amplifier in the what you call closed loop, but in the open loop, this value gain will be A naught itself. So the value here, maximum value here or here will be, sorry, either here or here will be. So here, when this is conducting, the voltage here will be 0.7. When this is conducting, the voltage here will be minus 0.7. So in either case, when we have here either plus or minus 0.7 volts, the input value will be, divided by this by A naught. So that means when the input is 0.7 by plus or minus 0.7 by A naught, then more than minus point plus or minus 0.7 by A naught, when Vi is more than plus or minus 0.7 by A naught, then we'll have here voltage which is more than plus or minus 0.7 volts, because that multiplies with A naught. And at that time, the transistors will start conducting. So therefore, thus reducing the dead band, and hence the crossover distortion to only a very small value. So the high gain amplifier tries to reduce the crossover distortion, but there's a disadvantage associated with it, and that is the slew rate limitation of the op amp will cause alternate turning on and off of the output transistors to be noticeable. So because there is what is known as slew rate. Slew rate is the rate of change of output voltage with time of the op amp, and this is limited. It's not infinite for the op amp. Because of this, the turning on and turning off of the output transistor will be noticeable, especially at very high frequencies. A more practical method is the use of class AB output stage, which almost eliminates the crossover distortion. So we will see later that class AB is the one which is responsible for eliminating the crossover distortion. The class B output, what you call amplifier, can use only a single supply operation, can what will be used under single supply operation. In place of VCC and minus VCC, we can connect a single power supply here, which is 2 VCC, and this can be grounded, and then we can use this by using a what you call here a RC load, okay. So then this will be able to remove the DC component, whatever is there at the what you call output side. Now let us take another example for a class B output stage of the figure, whatever is given. Let VCC is equal to 6 volts, RL equal to 4 ohms, and if the output side is 4.5 peak amplitude. So peak amplitude is given. So definitely the RMS value will be divided by root 2, and correspondingly, we should take the value. Find output power. The average power drawn from each supply. The power efficiency obtained at this output voltage. The peak current supplied by VI, assuming that beta N is equal to beta P equal to 50. The maximum power that each transistor must be capable of dissipating safely. So if we take over here, then we'll see that the first one, the output power, okay, is basically the load power, that is 1 by 2 V naught square by RL. So 4.5 square. So V naught square is 4.5 square by 2 into 4. That is what is given here. And we will get the value, which is 2.53. Similarly, PS plus and PS minus is the average power drawn from each supply, and that will be 1 by pi V naught by RL VCC. Okay, V naught by RL VCC. So if you find each one of this, we will get the value as 2.15 watt. So total power dissipated will be double of this, which will be 4.3. So we can find that. Then we can try to what you call find the efficiency corresponding to this, and that will be PL by PS. So that will be 2.53 divided by 4.15, and that will give us something like 59%. And then we have to find the peak current supplied by Vi, assuming this. So peak current at the output will be the value of IL, and that is same thing as IC. IC divided by beta will give us the IB, and that is the peak current supplied by the I. So peak output current is V naught by RL, and that is given by 0.5, 4.5 divided by the value of 4. The peak input current is peak output current by the beta value, and that is 4.4, 4.5 divided by 4, uh, and that is divided by again 50. So we will get somewhere around this value. Really speaking, we'll get 22.5 milliamperes. So then the maximum power that each transistor must be capable of dissipating, each transistor, that's why PDN max is equal to PDP max is equal to VCC by pi squared RL, and that value will just turn out to be 0.91. Together, if you want, then it will be double of this. So with this, we come to the end of the class B power amplifier. Thank you.